3, 31 over 6, 14 over 3, that appears to be a decreasing arithmetic sequence. And for this question, I guess like the context would be that this sequence is meant to count some set of real physical objects. And as such, negative numbers don't really make sense, right? You can't have -3 pens unless you owe the bank 3 pens or whatever. So at what n value does this sequence turn negative? Go ahead, figure that one out. And then item number 2, some non-COVID related news. Just because, I don't know, you would open any news source and it's always COVID stuff. And don't get me wrong, I guess it's like important to stay apprised as to that stuff, but at some point it's overwhelming, it's a bit of an overload. So get down the numbers that you need for that first question, and then I'm going to change slides here in a second. Anyway, this was one of the scientific discoveries, like a paper published after the lockdown stuff happened. And even though all of the world's scientists are now stuck at home, there is still a little bit of research to finish up, just because people have data from their labs that they threw on flash drives to take home to finish. I guess the sad part is that like scientific discoveries will probably stop trickling out in a few months because there was no data taken these last few months, except for a few exceptional cases. But you know, for the last month or so, there have been a few more scientific discoveries going out to the world. This is a cool one that I saw from last month. This animal is called the yellow-rumped leaf-eared mouse, which, you know, is very cute, obviously. But the reason why it's exceptional is that it is the world's highest elevation living mammal in the world. And not only is it the highest elevation, like, dwelling mammal in the world, but it also beat the previous holder of that record by almost 8,000 feet. Like, this thing just lives way higher up than we expected any mammals to live anywhere. It's really hard to be a mammal and function with, you know, that decreased oxygen, considering how much oxygen we go through just to maintain our body heat. But this exceptional little mouse figured out a way to do it.
There's barely any oxygen at 22,000 feet.
Yep, yeah, and this mouse just like hangs out there.
Jeez.
Yeah. Anyway, yeah, sorry to flip to my school email, but I want to make sure it wasn't something important about the start of the day. Anyway, yeah, let me take us back to the whiteboard. So yeah, deal with that item there, item number 1. There's a couple different ways that we could do it. Figure out one of them, and then we'll get into it. Today we'll be talking about section 3, geometric sequences, which are a lot like arithmetic sequences, where in an arithmetic sequence, every time we take a step, we're either adding or subtracting a number, which I guess is actually the same thing, right? Subtracting a number is actually just adding a negative number. But today we'll be talking about geometric sequences, where in every step, we are multiplying by a number. Oh yeah, and you know, as we come up to AP tests and finals, though the AP tests are much more pressing and, in my opinion, typically more difficult, right? Is it about right that the AP tests that you've taken have been harder than the finals that you've taken?
Definitely.
Yep. Yeah. Make sure to take care of yourself, because mental labor, like doing a mental task, is just as taxing as doing a physical task. One of my favorite numeric comparisons is like the fact that you burn 2,000 calories a day. Just basal metabolic rate, staying at home, doing nothing. Any amount of exercise that you do will lift that up. And extreme activities spend extreme calories. So like a marathon, sorry, I want somebody else to do the math for me. Yeah, okay, I'm not crazy, yeah. So when you run a marathon, when I ran one back in March, on that day, I probably burned closer to 5,000-ish calories. Because it's about 1,000 calories, a little bit more for every 10 miles, and it's 24 miles. So that extra 3,000 calories stacked up with the baseline 2,000 means a 5,000 calorie day to cross that finish line. However, it's not only like extreme physical activity that will burn you up, it is also extreme mental activity. A similar number of calories, approximately 5,000 calories a day, are burned by people who are in chess tournaments, and like not running to or from the chess tournament or whatever, but the act of competing in a chess tournament for 8 hours burns a similar number of calories to committing to a marathon. So, even as you are studying, make sure that you are caring for your physical body and not just your mind as you do that work. Make sure to stay hydrated, take breaks for physical exercise, and eat snacks or whatever to keep up with your nutrition. Because if you find yourself studying a bunch and also being hungry more, that's real. That's not illusory. I definitely, when I was studying for finals at UCLA, used to go to the dining hall and put down like 2 or 3 meals more than normal a day.
Mr. Robinson,
Yup.
when you prepare for a marathon, do you gain a few pounds?
That's an interesting question. Everybody does it different, and I'm not an Olympian, so take what like my regimen with a grain of salt. In the week, so I don't know, it's a year-round thing that I'm getting ready for. But 3 weeks before is where stuff gets weird. So 3 weeks before, I actually spend the 3rd week out fasting, and I lose a bunch of weight that week. I basically only eat dinner for that week, and even those dinners are small. And then after I fast all the way down, then over the next 2 weeks, I get back up to like normal weight, I guess, which most of the weight gained back is water. But no, not really. And it's not that, like on the day of, all of the additional 3,000 calories that you're burning aren't fat. Because if you were to like gain weight to do an event, like intentionally gain fat for you to burn later, the event is still going to be extremely difficult, because when fat gets metabolized to become usable calories, it goes through a process called ketosis, which is highly inefficient unless you're doing it a lot, and makes you feel sluggish and tired and all this other bad stuff. So most of the calories that I get on race day actually come from like eating during the event. They make these little envelopes of sugar that are like this, that are like 100 calories each, that keep your blood sugar up. So even while you're metabolizing fat, you are still also metabolizing a mouthful of sugar every like 45-ish minutes. And on top of that, people along the sides come from companies, and they'll also give out similar type sugary products. And the funnest part about the LA Marathon is that as you run through ethnic parts of the race, people are just on the sides giving out like food. Like as we ran through the Japanese part of town, there were people out there giving out like steamed buns, which was a huge relief getting out there towards the end. But yeah, for that type of endurance event, you like mostly eat as you go. You don't try to load up. Carbo loading is mostly a myth. Anyway, let's go ahead and get into it. So could I get some answers out there? What are we looking at here?
This is somewhere around like -12. The
we don't
12th term.
we don't want to
12th
be
term.
like talking around. We just want the answer. So what's our
12?
approach?
Find the difference.
Okay, yeah, so no matter what method you're going to do, you definitely start off by finding that common difference. And what is that common difference in this case? How much is being subtracted from there to there?
Is it half?
Half. So -half.
Yeah, so each time here, we're going to go ahead and subtract 1/2. The only thing is that, we, I guess, you can tell that the constant here that makes the sequence go has to be some strange number, which is why we're not sitting on nice, clean, like half values. But nonetheless, so we go here and we check out 17 divided by 3. And from this, we are going to subtract 1/2. And that works. If I hit math, frac, we can show that that works out. That gives me my next entry, 31/6. And here's a thing that I think is nifty. If I hit second answer and I subtract from that 1/2, what this is going to do, this instruction, is it is going to take this number from that, it will subtract 1/2, and then it'll give me the next value, right? And now I can hit second entry again, and since it's already pre-built in with the command answer minus 1/2, if I hit enter again, then it will automatically do the recursive version of the sequence. So if I just want to know, well, how many times do I have to hit enter until I get to some specific value? This is this will keep generating. It's as simple as second answer, enter, 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 all the way down until we get that desired negative value. And then we could have counted out from the top how many times I hit enter to get down here. Is that okay? So just kind of one weird trick that you can do with your graphing calculator for these sequence and series things. If you just want to quickly generate a list of values, you can use the answer command and the second enter command to have your calculator recursively generate the values one at a time. However, I'm going to actually solve out item number 1 a little bit more explicitly here. So what I'm going to do is I'm actually going to build the explicit version of the series. So this is to say that this is being generated out by -1/2 n plus some constant b that fixes our first value. Our first value is 17/3 is equal to -1/2 times 1, n plus this value b. And then I can get from this that b is going to be equal to some fraction, something over 6, right? So 17/3 plus 1/2, being lazy. And our fraction is 37/6. And so our explicit function here is going to be a is equal to -1/2 n plus b. I'm sorry, plus 37/6. Why would I do this? How could the explicit function possibly tell me, like, where does this series turn or sequence turn negative?
Wait, Mr. Robinson, is that a basic equation you just used?
Equation?
Yeah, like a equals -1/2 n plus 37/6.
Yes, this is a sequence generator for an arithmetic equation. The sequence generator for an arithmetic sequence is always a linear equation.
I don't know which one was a n plus 1 minus d.
That is the recursive equation. So this is the explicit equation, but from this information, one could generate the recursive equation in the following form, which is effectively what I did on my calculator. That is to say, tell me explicitly that the first a is 17/3 and that I get all the other a's based off of the previous a by subtracting 1/2. This would also generate it out, but this isn't as useful for finding where a sequence turns negative.
Okay.
In this case, we're turning negative at a fairly low number, but if we were turning negative at, let's say, the 10,000th entry, then you don't want to hit enter on your calculator 10,000 times. That's why I'm offering this approach for finding where a sequence changes sign. At what value do we change signs? What number must you cross to go from positive to negative or negative to positive?
0.
12.
0, and that's the key.
Or yeah, 0.
So
yeah.
if you want to know where some sort of sequence changes signs, in this case, we started off positive, but as we're going to the right, we go negative, 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 negative. Or if we had some sequence which started off negative and was headed in the positive, 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 positive direction, you set it equal to 0. In both of those cases, you are crossing the y-axis. And so if we know where this sequence hits 0, we will know where this sequence changes sign. So really quickly, solving for n, I would subtract over 37/6, and then I would multiply both sides by 2. So it would be -37/6 times -2/1 would give me n. So 37 times 2 divided by 6 gives me that n is equal to 12.33 repeating. So how do we interpret that? What's our first negative value? What n?
The 13th?
13.
It has to be 13, because this is saying that if we could put in n with a fractional amount of 12, then that would give us 0. So the next value has to give us the negative value. So n is equal to 13 in this case. Or if you did it recursively, it's probably because you started at 1 and then you took 12 steps to get to that negative number. But you're starting at 1, so 12 steps later, you're at 13.
Oh, okay. Yeah, that's what I did. That's how I got 12 because I did it recursively.
Yeah. So just keep in mind that your first position was 1, not 0. So 12 steps from 1 leaves you at 13.
Okay.
But yeah, I hope the thing with this was cool, like using answer and that number so that you're not punching in a bunch of numbers every time. Just a quick reminder that if we were just doing counting numbers, 2 plus 1 gives us 3. Answer plus 1 gives us 4. And then, and then plus 1. And then this, makes our calculator count for us. It's a super useful trick. We'll look at it today in our next section of notes.
Mr. Robinson, can you go back down
Yeah.
a little bit? Thank you.
Mm-hmm. And I mean, it is, you could just mash enter and it'll keep going with the sequence. Super useful for this chapter and for statistics when you guys get there. Anyway, today we'll be doing notes on section 11.3. Today we'll be talking about geometric sequences. Today, oh, my pen. Today we're talking about, oh man. Also, I ordered a new, so I ran out of black ink, the whole house out of black ink. And I ordered a new pen cartridge from Amazon. Because of various labor disputes and other supply chain disruptions, a pen cartridge that was supposed to get delivered yesterday for this pen just got delayed 10 days, man. I thought I'd be back to black ink today, but no black ink until after AP test, it seems. Big sad. 11.3, geometric series. Okay, so you're going to notice a lot of parallel structure between what we talked about before and what we're going to talk about now. So a lot of the same vocab exists. It's just that the mathematic definition of what's going to be present in each one is going to be modified, However, all of the vocab exists, but the definition of each one of those vocab terms is going to be different here in terms of what the equation ends up being. So a geometric sequence is something of the form, and this is a really common one that you're going to see a lot, especially those of you who are headed into computer science. Let's go ahead and say that we have the following sequence: 1, 2, 4, 8, 16, 32, So you'll notice here that if we were to attempt to find some sort of common difference, you are going to be disappointed. That is to say, to go from here to here, I have to add 1. To go from here to here, I have to add 2. So that means that if we were trying to talk about some sort of set of common differences, plus 1, plus 2, in this next jump, we would have to add 4. In this next jump, we would have to add 8, etc., etc., etc. So if you look at that series of common differences, right, they are increasing as we head off to the right. And there's not a generalized way that you could write down a linear equation that does this. It's literally not possible. Now, proving that it's not possible is complicated. That's harder math. So for us, if you attempt to find a common difference and it isn't actually common, that you're adding a different number every time, it means that the series that you are looking at is some type of non-arithmetic object. And I'm sorry, I keep like garbling these two. I didn't mean to say series. We'll be doing series in section 4. I meant to say sequence. Nonetheless, what other pattern do you notice here?
Multiplying by 2 each time.
Each time, what we're actually doing, the thing that remains common is we multiply by 2. we multiply by 2, we multiply by 2, etc., etc., etc. And so that's what makes it a geometric sequence, is that every time we step forward through the sequence, so each movement forward multiplies the previous value by the same term. Or I guess by the same factor. Right? So instead of stepping forward by adding or subtracting, we're stepping forward each time by multiplying. And so we're going to define out a couple bits here. The first one is what we call this common factor, and for whatever reason, we don't call it factor or coefficient or any of the other fancy words that we've invented up to talk about numbers. We actually call it the common ratio. And the common ratio is defined as the following. The common ratio is typically just called R in this case, where R is equal to the next value divided by the previous value. This is to say, if you want to build this out, this is going to, this is going to be A sub n plus 1 divided by A sub n. All that this is saying is that if you want that common ratio, whatever it is, you take the next value and divide it by the previous value. So 8 over 4 would give us 2, 4 over 2 would give us 2, 2 over 1 would give us 2. This is defined in kind of a backwards way. This is a really useful term, though, because this lets us write the other vocabulary that define a geometric sequence in its own terms. And here's a couple of them. This means that our sequence is going to be equal to whatever our first term is, a sub 1, and then what generates the next term. What would we multiply this by to get the next term? To get the next term, we multiply by our common ratio. So this next term will be a sub 1 times r. And then what's the next term?
Is it still R?
If it was a sub 1 r, it would be the same number repeated again. Sequences don't typically repeat values.
Is it a sub 2r?
So this is a sub 1, this is a sub 2. So this is saying that a sub 2 is equal to a sub 1 times r. So you are correct. I could call this next term equally a sub 2 times r, but for the sake of argument, let's leave everything as a1.
So a sub 1 r.
What's r times r?
R squared.
R squared.
There we go. That's a much more common way to talk about that. So then what's our next term in the sequence?
A sub 3. So then a
R
sub
cubed.
r to, yeah, power of 3.
A sub 1 r cubed, which would actually give us back a sub 4, etc. So how is this growing as we increase in value? What do we typically call this type of growth?
Exponential?
Yep, geometric sequences exhibit exponential growth, which we'll come back to soon because exhibit exponential growth. The same way how arithmetic sequences exhibit linear growth, but they're technically not lines, the same distinction exists here within our geometric sequence. And so geometric sequences actually have a really pretty way of writing the recursive relationship. In order to write the recursive relationship, all we do is we take the definition of the common ratio, multiply both sides by a sub n. So if I were to multiply both sides by a sub n, this would tell us that a sub n plus 1. So the next term in any given geometric sequence is equal to the previous term in the geometric sequence, then multiplied by r. This thing and this thing are the same thing, just multiplying both sides by a sub n. So this right here is the recursive formula.
Wait, Mr. Robinson, shouldn't it be r to the power of n?
No, this is saying to take one step forward. To take
Oh,
a
okay.
single
This
step
is
forward.
recursive.
This is
Okay,
recursive, yeah.
Okay.
So going from n to n plus 1, just multiply by r, and that rule works all the way across, times r, times r, times r, times r, times r.
Okay.
But yeah, that leads us to our explicit form, which is going to take the following form. And that's why we actually listed out these terms up here, so that it's really, quick and easy to see the explicit formula. So if you want any general a sub n, this is going to be equal to the first a1, then multiplied by the common ratio raised to a power. Let's go ahead and look at what that power is. So when n is 2, what power is this being raised to?
1,
When n is 3, what power is this raised to?
2. So n minus 1.
It's got to be n minus 1. Yeah. And this gives us the really nice feature that when I plug in 1, 1 minus 1 is 0. And what's r raised to the 0th power?
1.
It's exactly 1. So then that first term is just a sub 1 times 1. So this right here is our explicit formula.
Mr. Robinson, for the recursive form, don't you have to write one of the terms of the sequence?
Oh, sure. Yeah, that's always true for a recursive form. So you would have to combine this information along with a fixed point. You would have to also give some A1 or A2, or any A would technically allow you to fix that point. Yeah.
Okay.
And so the same distinction that we had to draw with an arithmetic sequence was the fact that while it has an exponential formula to it, that it is not exactly the same as an exponential equation. So if I were to have the equation y is equal to 3 times 2 to the x, this will give us some like nifty shape that we could figure out real quickly. So I would draw my axes. The variables here would be x and y. And then in order to graph this, I would want to fix a few points first. So first I want my intercept. So that'll give me y is equal to 3 times 2 to the 0. So y is equal to 3 at our intercept. So this is telling me that one of my intercepts is 0, 3. And then my next point would be y is equal to 3 times 2 to the 1. So then y would be equal to 6. So this is telling me that another point here is 1, 6. So I can now really quickly and correctly graph this. I have an intercept of 0, 1, 2, 3 right there. My next value is 1, 6. So 1, 2, 3 higher than that. And then this thing is exhibiting some sort of exponential growth as we move forward. So it's going to come in, go up, and then just keep going up. So that's my exponential graph. And if y'all don't remember the parent functions for exponential graphs, they do this. So they have a domain from -infinity to infinity. They have a range typically from 0 to infinity, depending on exactly where that asymptote is. And here's why I talk about this. If we had some sequence, a sub n is equal to 3 times 2 to the r, and then we started listing out the possible values of this. Our first value is going to be 3. I'm sorry, r heck, 3 times 2 to the n minus 1. Anyway, so we plug in 1, and it's going to be 3 times 2 to the 0, which is 3. And then the recursive formula makes it easy to figure out what these values are going to do as we move along. So 3, then 6, then 12, then 24, on and on and on and on forever. And so here when I graph it, what's going to be different about this graph?
It's going to be just a bunch of points.
It's just a
Right,
bunch of dots, because we're not actually, you can't actually like logically generate what would happen if you were to plug in n sub 1/2, because by law, when it comes to these sequences, those n's, they must be counting numbers. They must begin with 1. So one small distinction here to observe. One small distinction here to observe is that this is n versus a sub n. And our very first value that could exist is that when I plug in 1, I get back 3. And then when I plug in 2, I get 6. And then when I plug in 3, I get 12, which is already off of the graphing zone. It would like be up here. But that's it. So while these share output values, they share values and behavior. They have different domains and ranges. So like the mathematical object we're playing with that generates out this geometric sequence, technically the explicit form of it is some sort of exponential relationship. However, it itself cannot technically be defined as an exponential function. And then the last thing that I want to talk about real quick is that the same way how exponentials need 2 different parent functions, we need one to talk about exponential growth and one to talk about exponential decay. Geometric sequences can either be increasing or decreasing. So here are some important notes about different types of geometric sequences, different properties that R can have. Is it okay if I turn this page?
Yeah.
Okay. Okay, so 2 important features to look at when it comes to the common ratio R. So if the absolute value of R is greater than 0, then the absolute value of the sequence grows as we increase R, right? So that's pretty obvious. That's like that first basic part of our warm-up, where R was, I'm sorry, if R is greater than 1, yeah. So if R is greater than 1, if we're multiplying by some number which is bigger than 1 every single time, then the absolute value of the geometric sequence is going to increase as we head to higher and higher and higher and higher n values. This would be considered an increasing geometric sequence. If R falls into this second category, and I'm going to state it this way because this is the mathy way to state it. Can somebody explain to me what that means?
R would be a fraction.
I like that. That is the cleanest way to state it. So if R is a fraction, specifically if R falls between 0 and 1, then the absolute value of A, and this is a really specific thing I'm going to say here, asymptotically approaches 0. That's our exponential decay model. So this would be a decreasing geometric sequence. But it specifically asymptotically decreases towards 0, typically. You're going to get an approach on the axis when R is fractional. Divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. The number will keep getting smaller, but it can't cross the 0 line. And then the last one is weird. So if R is less than 0, what does this mean?
Negative.
This means that it's specifically negative. So notice up here, I talked about the absolute value of it, but here I'm talking about the sign. So if R is strictly less than 0, then the sign of A sub n oscillates with each step. It's going to flip back and forth from plus to minus, 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 plus to minus. Now, this piece of vocab that I'm going to give you is not what the book calls this, but when we use this type of mathematical object in physics, we don't like it because we say that this is a chaotic geometric sequence. There are a bunch of very useful properties that geometric sequences have that you can exploit when solving problems, but having a negative common ratio tends to be a bad approach in any problem that you are trying to model. These behave chaotically. There are several operations that you cannot do with these sequences that you can do when that common ratio is positive. So real quick, I'm going to just sketch out the 4 different possibilities, and then we'll look at a simple example question. I'll hold the fancier example question for our next class on Friday. So we're just going to do a real quick Punnett Square. And so the point of this Punnett Square is to try and capture the 4 possible combinations here of what our geometric sequences typically look like when we graph them. Just so that you know what to expect with your digits when you are analyzing these 4 different types of geometric sequences. So on the top here, we're going to have our condition about the absolute value of R. So is R a big whole number, or is it some sort of fraction? So here, this is going to say R, the absolute value of R is greater than 1. And then over here on the right, we're going to have our fractional option. So that is to say that the absolute value of R falls in between 0 and 1. And then over here on the left-hand side, we're going to have our conditions for signage. So up top, our usual case where R is positive, that is to say R is greater than 0. And then down here, we are going to have our signage that shows that R is negative. So if you don't like the way that this is written, feel free to write the words out. So R is a big number, R is a fraction, R is positive, R is negative. This is just like the mathy way to define these conditions. So for this first one, this is, I think, the most obvious one. We have a increasing geometric sequence and R is positive. So this is the same as the one that we sketched before. We're going to get a bunch of dots that trace out an exponential curve. Over here, if we were to graph these out, we are going to have a bunch of dots that represent a decreasing exponential curve. But keep in mind that they zero out, they asymptotically go to 0. They can't cross into the negative region all on their own. Down below here, we are going to have R is greater than 1. However, R is negative. So while the absolute value is going to keep increasing, we are going to get this nightmare plot. And for this one to work out, I'm going to draw in the axes. Up here, I guess I'm treating the box as the axis, right? So all of this is occurring inside of quadrant 1. And 4, I guess it had a negative region. All of this is occurring in quadrant 1. But down here, we'll have to consider quadrants 1 and 4. So every time we step forward here, right, this is going to make the absolute value get bigger, but it's negative. So that first time I multiply in, we could get a positive number. And then the next time I'll get a bigger negative number. And then the next time I'll get a bigger positive number. And then at the next time I'll get a bigger negative number and then a bigger positive number. So you can't connect these dots with any sort of logical line. You basically have 2 separated exponential trends, one that goes down, one that goes up. But depending on whether or not the n that you're selecting is positive or negative, that will decide whether or not you are in the positive or the negative region. This is a very poorly behaved mathematical function. The same is true over here. We're going to have both features. The absolute value is going to get smaller every time, but also every time the sign will flip, depending on whether or not the n that you are selecting is odd or even. So we're going to have some big positive number, and then the next step will be some big negative number, and then some big positive number, and then some big negative number, and then some smaller positive number, a smaller negative number, a smaller positive number, a smaller negative number, a smaller positive, a smaller negative, back, forth, back, forth, back, forth, back, forth.
Mrs. Robinson?
Yep.
These are all considered chaotic sequences.
Both of these are types of chaotic sequences. Yeah, there's a bunch of math that you wouldn't want to try and do with those. Like next year, you guys are going to learn some new operations that calculus lets you do. And if you were doing those calculus operations here, you could do them on these nice and easy. If you were to try to do those calculus operations down here, you would get wacky stuff like infinity divided by infinity to the 0, or 0 to the 0 divided by infinity. You get a whole bunch of nightmare objects that you can't actually touch or learn anything about. Okay, so that's it for the vocab talk notes about geometric sequences. They're a sequence where every single time we take a step forward, we're multiplying by a digit, and that's it, aside from like all the details in the graphing and the outcomes of possible values of R. Let's do one quickie example, and then we'll get out of here, and I'll post the homework, and then I'll see you guys on Friday, because like I said, tomorrow you have day off because I have a 6-hour test to take.
We have a final tomorrow?
Dude,
What?
Comprehensive exam.
What are you guys talking about? You guys have a test tomorrow?
No, I was asking, like, is it a final tomorrow that you're gonna take?
No, I for us,
Proficiency.
final start the week after. Tomorrow is my exit exam.
yeah, good luck, Mr. Robinson.
Good luck.
Thanks. I don't need luck, but thank you for the well wishes. Yeah. So let's go ahead and say that we have the following geometric sequence. I have, for example, here, b sub n is equal to the following set of values: 16, comma, -4, comma 1. You know, technically, I shouldn't put that second brace on until I put ellipses. Technically, the ellipses are important because they mean you go on forever, ... And so all that I want here is I would like the explicit, recursive, and give me b sub 100. And so this is as straightforward as it is for doing this work for an arithmetic sequence. The only difference is we're not looking for a common difference. Now, we know that this is an arithmetic because the difference from here to here is 20, while the difference from here to here is 5, so that doesn't work. So what does it seem like our common ratio is?
-1/4.
Yep, to get that common ratio, all we have to do is take any term and divide it by the previous term. So -4/16, -1/4. 1 divided by -4, also -1/4. And so what we're doing each step here is we are multiplying by -1/4. We are multiplying by -1/4. And so our recursive formula is real straightforward. Our recursive formula is simply asking us to take the previous term, so to go to a sub n plus 1, based on a sub n. What do I multiply by?
-1/4.
-1/4.
So that's
Yeah,
part of our
-1/4.
answer. And then here's the explicit form, which is also nice and easy. A sub n must be equal to our first term, which in this case is 16, multiplied by that common ratio, -1/4, raised to the power of n minus 1. If every single step that we're taking, we're multiplying by the common ratio, it's got to be some sort of exponential function with this behavior. So I plug in 1, 1 minus 1 is 0, anything to the 0 is 1, first term is 1, 16, and you can show very easily that this is going to generate the rest of the terms out. That makes it so that instead of generating all of these terms out and pressing enter on my calculator 100 times, instead I can just say that b sub 100 must be equal to, sorry guys. I've been kind of sleep deprived lately with all the like cat medicine delivery and cramming for this exam. I'm not on my best game today. Anyway, b sub 100 has to be equal to 16 times negative 1/4 raised to the 99th, right? Because it's going to be 100 minus 1 up there. And so we could take this and we could feed it to our calculator. I don't even know if your calculator will take this. I think it might be too small of a number for it to ring up. Oh, it did it. And it's too small to express it as a nice clean fraction. That's a shame. So I would take this, or I would take the following, negative 3.983. What does this mean? E to the negative 59?
Isn't it to the power, like to the power of negative 15? Oh no, times 10. Times 10 to the.
Scientific notation.
Yeah, it's scientific notation. So it's times
10.
10 to the negative 59, which means it's
Yeah.
actually 59 zeros and then the 3. So first there would be 59 zeros to write out, and then you get a 3, which is to show that if this thing is a decreasing geometric function, it exponentially it asymptotically approaches 0. So this is a crazy small number. This is like as close to the y-axis, as close to the x-axis as you can get without touching it. Is this okay? So just based on these 3 digits, we were able to quickly generate the 3 pieces of our answer.
Mr. Robinson, for the recursive form, could you written a sub n is equal to negative 1/4 a n minus 1? Would that be the same?
Those are exactly the same, and you'll notice that it gives, yes. So this is always the same thing as this was b sub n is equal to negative 1/4 b to the n minus 1. This is still just saying these two terms are spaced by a difference of 1. If I were to say n equals 4, 4 plus 1 is 5, and then this over here is 4. So the 5th term is based on the 4th term. If I were to say here that n is 5, then this would tell us that the 5th term is based on the 4th term. It's the exact same information.
Okay.
Typically, shifts of constants in equations don't change their meaning or behavior.
Okay.
Anyway, like I said, y'all have tomorrow off. I'm just going to post the homework, and then it won't be due until Friday night. We'll go over it on Friday. And then I believe we're taking some time off so that y'all can deal with AP tests. Let me see how much time I'm giving y'all. Oh, no, I lied. You guys don't have your first test until the end of next week, right?
Yeah.
Yeah. So I'm going to take that homework from you guys tomorrow so that you don't have any homework to deal with over the weekend. Man, Google Docs is slow right now. Yeah, and then next week, we have one more section to do, 11.4, where we'll talk about series, which is a more interesting thing to calculate. And then I planned a quiz next week, which your guys' AP test isn't until Friday, so you would still have Thursday to deal with it. But think about whether or not you want the quiz before or after AP tests, and I'll let you guys vote and decide. Like, if I was you, I would just do it and get it out of the way so that it's not hanging over you during AP tests. But if you guys want to push it until after AP tests, that's fine. But that just means that you'll have to review stuff that's weeks old after doing all that testing. Like I said, the current plan is to just have the chapter quiz next week on Wednesday before we stop for AP tests, but I'll let y'all vote. You all have a very nice day, and I will see you on Friday.
Bye, Mr.
See
Robinson.
you, Mr. Robinson.
Peace.
Good luck tomorrow.
Thanks.
See you.
Good luck.
Bye.